All right, we're rolling. All right, so I'm going to do sort of two variations of a Newton's second law lap, then we'll get into the centripetal motion. So start out with, I've got obviously a triple beam balance here. We're going to find out, I'm basically going to hook the mass to the end of the string. We're going to figure out what the acceleration is and see how well it matches prediction. So the basic setup, I have a table, I have a cart, pulley, hanging mass. So this is mass of cart, mass, so H for hanging. What would you expect the acceleration to be? Well, let's go through the steps. I got the cart, I got the mass here, the hanging mass. What are the force diagram?
Gravity off of the masses.
Be more specific.
Gravity downwards.
Okay, that is more specific. Keep going. Be more specific.
Wait.
Thank you. All right, so weights of cart and weights of hanging. Okay.
Normal force down from the cart onto the ground and then back up.
Okay, so it's down on the table and or track and up on the cart?
Yeah.
Okay. Sorry? Yep, going which way on the cart? Okay. And which way on the hanging mass? I've seen fingers pointing up and down. It is indeed one of those two. I now see two fingers going up. It is indeed. If I cut the string, this mass is just going to be in free fall. So the string is keeping it from falling in free fall. That tension is acting up. We are assuming that the mass of the string here is negligible compared to the other masses, so I'm not going to worry about that. That also makes it a calculus problem, so, and I'm not going to worry about that. Sorry. The more complete thought is, if we did consider the mass of the string, it would become a calculus problem. So this is what we're working with here. Also assuming that the pulley is, mass of the pulley is negligible, and that the friction on it is negligible as well. This is one of the things that are labeled as a super pulley, and it does spin for quite a while without stopping. All right, so there's the force diagram. Acceleration. Which way is the cart going to accelerate?
To the right.
And the hanging mass? We are assuming that it's an ideal string, and therefore their accelerations would be the same, because they would move the exact same distance in the exact same amount of time. They'd be going the exact same speed, etc. All right, coordinate axes. What would be a nice coordinate system set up for the cart?
I have J hat. Or other way around. I have J hat.
Okay. And I'm going to put a little seat down here and there. And what about for this guy?
Just J hat down.
Put a little subscript H there for hanging. Another sag marker. All right. There's my coordinate system. Decomposition. Do I need to break any vectors up? Are there any vectors that are not parallel or anti-parallel to my axes? Pardon?
Can you explain what that means?
When I set up my equations of motion, if I have a coordinate system like this, and I have a vector that's pointing like that, then part of it is horizontal, part of it's vertical. I would need to break that up. So what I'm doing at this stage is seeing, is there any vector that is not, in this case, horizontal or vertical, and in this case, vertical? I got my three vectors right here. Any of them not horizontal or vertical? In this case right here, any of them not vertical? Okay, so we don't have to break anything up. Now my equations of motion. How many equations of motion will there be? All right, we'll have an I sub C equation, a J sub C equation, and a J sub H equation, one for each axis. So what are the equations?
I sub C equals tension. Or
Wait, say it again?
I sub C equals tension.
Oh, okay, so I have tension.
Equals mass times acceleration.
Like that?
Is it supposed to be vector acceleration
The vector piece of it is already taken into account here. We could stick a vector after all of them, but they're all the same vector. That's why we're setting up the equations this way. There's potentially a problem with this equation, but we'll find out in just a moment. All right, what's another equation?
I'm gonna be honest, I don't
You don't see where that one comes from?
know.
All right, so when we're doing equations of motion, we're plugging into Newton's second law of motion. The fact that the total force is equal to mass times acceleration. This is the basis of all of this. That's our template. So we go to this equation right here, we're looking at the horizontal forces. All the horizontal forces, that's the only horizontal force. So that's my total horizontal. That's where the FT comes from. And so that's gonna equal to mass times acceleration in that direction.
But I thought in the D portion, we said that there was no horizontals, but you mean as in crossing, right?
So ask your question again?
When you explained to me what D was, that's only if the horizontal is crossing something else.
If there was something that wasn't horizontal or vertical, we would break it up so for instance, if we had the box on ramp, if we set up our coordinate system like this, I know weight is acting down on the box. It's not in the direction, it's not in either of those directions. So I have to break it up into a part that's in that direction and opposite that direction. We want all the vectors to be broken up so that they match whatever coordinate system we come up with. Here, since we have a horizontal and vertical, I'm trying to figure out, is everything horizontal or vertical? Here, since I have an axis parallel to the ramp and perpendicular to the ramp, are there any forces acting on this that are not parallel to the ramp or perpendicular to the ramp? Well, weight is not. So that's why weight has to get broken up. And then there's a normal force acting that way. When we break weight up, the part down the ramp is the weight times the sine, so this angle down here is theta, times the sine of theta. This is W cosine theta, and then normal force. At this point, we now have all the forces that are parallel to the ramp and perpendicular to the ramp. We can now do our equations of motion. It's not a happy look I'm seeing over there.
You lost me with the cosine thetas.
About where those come from? We've done one of those in class, but if ever I'm breaking something up, if I'm breaking this up into horizontal and vertical components, I want a right triangle with where I know one of the angles, besides the 90-degree angle. Whatever I'm breaking up is a hypotenuse. So, like in the projectile motion problems, if this is 50 meters per second, and that's a 30-degree angle. Then I'm breaking it up into my horizontal and vertical pieces. That the adjacent side here is cosine, so that's 50 meters per second times the cosine of 30 degrees. And the opposite side to that angle will be the sine, so that's 50 meters per second times the sine of 30 degrees. So I'm taking my vector here, just breaking it up into pieces that I can work with much more easily. There's a good bit in that 3 disappeared for whatever reason. So when we're trying to set up equations that are much more easy to solve, much more easily solved mathematically. And that's the point of decomposing if we have to. We just don't have to in this case.
Thank you.
I feel like I still haven't quite nailed it yet, but we'll be doing some more examples. That's supposed to bring the smile to your face. All right, more examples. There we go. That's a very sincere smile. So when I'm doing the equations of motion, all right, so for example, the vertical equation of motion, the JC one. You tell me all the forces that are in the positive J direction.
All the force.
Yeah, I got one that's in the same direction, that's in the positive direction, so I write down my normal force. There are no others. Minus, what are all the ones in the negative direction? I've gotten all the forces taken care of, so that's going to be equal to mass times 0. Yeah. Because the acceleration is that way. There is no acceleration this way for this guy. And then the last one, and then I'll do the equations of motion slightly differently to see if that way makes more sense. Boy?
Would J sub H be F sub T minus W sub H?
So F sub T minus W sub H?
Yes.
What are you gonna set that equal to?
W sub H times acceleration.
Then there's gonna be an issue if you do it that way.
Okay.
So would it be the tension, like the F sub T is equal to W sub H times acceleration?
No,
So W sub H minus tension equals mass times acceleration.
that's not close.
So I just got it backwards.
Yeah, if you said up was positive, which is in essence you did when you said F of T minus W sub H, then you'd have to have negative A as the acceleration. So W sub H minus F sub T is equal to, you said mass times acceleration? All right, there's now an issue with the way these equations are written. It's an easy fix, we're not gonna have to erase anything.
Should we have added the, like, mass of cart?
Yes.
The hanging mass?
These masses are not the same. This is the cart, and this is the hanging mass. Now, the normal force in this particular case, that middle equation, doesn't really matter to us. If we had some friction involved, it would, but we don't. So I'm looking at these two equations. Oh, substitution, that's the next thing. Do we have an independent equation for any of these variables here?
Tension.
Right?
Tension.
What is the independent equation for tension?
Tension equals mass of cart times acceleration.
That's not always true.
Oh, okay.
I'm looking for a separate equation that is always true.
Weight equals mass times gravity. Or the acceleration due to gravity.
Thank you very much. Yes, that's the one. we have a separate equation for weight. So I got tension is equal to mass of the cart times acceleration, and I'm not gonna bother with the second one. And then we have mass, hanging mass times acceleration due to gravity minus tension is equal to mass, hanging mass times acceleration. All right. Now solve. We're solving for acceleration. How do you solve it?
Can you just divide that side by the mass and move it over?
Say, out louder, please.
You just divide the mass by the right side and move it over.
So move the mass over
Yeah.
on which equation?
Bottom one.
So divide by mh,
Yeah.
and then what?
Then it's equal to the A, the acceleration.
Okay, we could do, all right, you wanna do it that way? I will tell you a hint, that's not the simplest way, but
Okay.
we can go for it. So the second equation, divide by m sub h, so I get g minus tension over m sub h is equal to a. Let's set that for a in the first one, I assume. So tension is equal to mass of carts times g minus ft over m sub h. Now what?
Can't get you any farther than that.
So,
Was the simpler way to substitute MC of A for tension in the second equation?
yeah. We're trying to find acceleration. I don't really care what the tension is. So doing it this way, you're solving for tension. You'll have to, basically you'll distribute, get the tension terms together, factor tension out, divide by whatever that is left over. Since I'm trying to solve for acceleration and not tension, it's probably easier to substitute tension and get that out of it. Or just add the two equations together would also work. But if we make that substitution, I get mhg minus mca is equal to mha. Now what?
Now I'm gonna divide.
Probably should do something else first before we divide. What are we trying to find?
Acceleration.
So let's get all the terms with acceleration on one side.
Could add that one.
Okay. So I have mhg is equal to mca plus mha. And now?
Is it stated in the problem, like, it's on Earth, so we can use?
Well, at this point, yes, it will ultimately be on Earth, because we're gonna do it right here. However, it's generic at this point. I could, if this were a test problem, I could quickly change it to Mars, and nothing we've done has changed. We're solving for A. I got two things with an A in it. How do I get just a single A?
Would you be able to like combine like terms?
In a sense. So what are you thinking?
Like if you did like m squared h or something, I'm not quite sure.
Or suppose it were 50 is equal to 5a plus 3a. What would you do there?
Combine like terms would be 8a.
Yeah. So you're gonna do something similar there. In essence, you're factoring a out. So you get mhg is equal to mc plus mh times a. In essence, that's what you do here. You factor a out, you're left with 5 plus 3, which is 8.
But you wouldn't make it a squared.
No. Because if I distribute with the other direction, it's a times this and then a times that. All right, so we now have an equation here. So A is equal to mhg divided by mc plus mh. Now, there are shortcuts that can be taken, but this is a process that we're going over here. The shortcut in this particular case is F equals ma, so acceleration is force divided by mass. That's the driving force right there. That's the force that's causing the whole thing to accelerate, divided by the total mass that's moving. So let's see how accurate this actually is. I've got what they claim is a 200 gram mass here. The triple beam balance is off by 0.38 grams. So offset 0.38 grams. I put this on here. Should be somewhere around 200, so let's see how close we get. Looks like it's slightly above. Wow. The measured mass here, so that's going to be the hanging mass. I got a measurement of 200.38 grams. It actually is printed correctly, or there's enough dirt on it to offset whatever it was off. So my hanging mass is 200 grams. But because we're cooling here, we wanted kilograms. How many decimal places? So 0.200, actually. Because we did measure out to that level of precision. All right, that is going to be the hanging mass. The mass of the cart, because it has wheels,